Hello, everyone. Um, I would like to thank the organizers for giving me the chance to speak here. I'll be talking about how we can extend the reach of the Cosmological Collider. This is based on and work with Raman Sundaram, which appeared here, and also with Arushi Podas and Raman, which we hope to finish very soon. All right, so with that, let's get started. So when you look at the CMB or large scale structure, we see fluctuations, and the era of cosmic inflation in the very early universe is one of the leading paradigms by which you can explain these fluctuations. And you basically say that all these fluctuations, they come from fluctuations of an inflaton field. And if you look at the simplest models of inflation, they say these fluctuations, they should be almost scale invariant, adiabatic, and Gaussian. Okay, and all of these three properties, they have been verified to a very good accuracy by the Planck collaboration. However, if we are to see any sort of violation of these properties in future, that would indicate that some non-trivial physics is going on during inflation. And that's why these three properties, they are very useful benchmarks by which we can search for new physics during inflation. In particular, we'll focus on this talk on this property where deviation from Gaussianity, in other words, non-Gaussianity, can be used as a probe of new physics. All right, so with that, let's just set the stage for, let's just set the notation. So we'll quantify as usual the primordial non-Gaussianity. We'll denote it by a function f, which is basically a ratio of the 3-point function to the product of 2-point functions. And as a result, the function f is dimensionless. And here, the primes, they basically indicate that the momentum conserving delta functions, they have been stripped away as usual. We'll also often be interested in the so-called squeeze limit, in which one of the momenta is much smaller than the other two. And furthermore, we'll use a gauge in which we don't have any metric fluctuations, but rather the curvature perturbation is given only in terms of the inflaton fluctuations and the inflaton velocity. Okay. A couple of last two things. So we'll work on leading order in slow parameters, and also often use the Hubble equals 1 unit, okay, which can be restored by just dimension counting. All right, so as many of you know, a very interesting type of 3-point function can arise if you have Hubble-scale particles during inflation. What can happen is that these particles, after getting produced, they can decay into inflationary fluctuations, which I'm showing by the solid line here. And also here, I'm setting one of the fluctuations, one of the inflaton field to its background value. So this leg does not carry any momentum. So what this diagram is saying is that after getting produced, this particle decayed into inflaton fluctuation. And as a result, it can imprint a non-Gaussian 3-point function in this particular case. And what's very interesting is that when you look at this 3-point function in the so-called squeeze limit, in which one of the momenta is much smaller than the other two, then in the squeeze limit, the 3-point function can have a non-analytic piece in which the exponent here is determined by the mass of this particle. Okay. However, along with this non-analytic momentum dependence that's dependent on the mass, there can also be a spin-dependent angular information. So here, depending on the spin s of the particle, you can have specific angular dependencies where theta is basically the angle between the short and the long mode. So what this basically tells you is that by observing the non-analytic momentum dependence and by observing the angular dependence from future data, we might be able to extract the mass and the spin information of this very heavy particle with masses of the order of Hubble scale during inflation, if those were to contribute to via diagrams like this. Okay. And since the Hubble scale during inflation could be as high as 10 to the 13 GeV, this is a very exciting probe of very high scale physics. And because the extraction of mass and spin are so similar to how we extract them in the context of terrestrial colliders, by basically looking for poles and so on, this has been dubbed as Cosmological Collider Physics program because here everything is operating on a cosmological scale. So, of course, there has been a lot of work on this recently. Here is only a small subset of the work. However, one caveat with the Cosmological Collider Physics program is that if the mass of this particle is much smaller than 1, then the non-analytic momentum dependence is somewhat lost because this exponent becomes vanishingly small. And at that point, it becomes harder to extract the mass of this particle. And furthermore, if the mass of the particle is much bigger than Hubble, then in that case, you basically encounter Boltzmann-like exponential suppression. Okay, so here I'm plotting the FNL as a function of m, and you see that very quickly you hit the exponential suppression. So the main idea of the talk would be, given this exponential suppression, are there ways of avoiding it? And also, can we broaden the scope of the Cosmological Collider program such that even loop level particles, or even particles with charges which would mediate non-Gaussianity only via loops, even those are observable, okay? So we'll basically try to answer these couple of questions in the rest of the talk, and let's now actually move on to that, okay? Okay, so having set the stage, let me just give you the outline for this talk. So first I'll talk about the theoretical setup in which we'll see that even particles with masses much bigger than Hubble, they can give rise to observable effects, and I'll show the results there. And after that, I'll also describe a scenario using the curvaton mechanism in which we'll see that even charged particles can mediate observable loop level non-Gaussianity. Okay, so let's start with that. So just to give you a bit more information, so typically during inflation, the space-time expansion, it naturally provides you a Hubble-scale energy. And that's why it's very natural to expect that if you are trying to produce a particle which has mass much bigger than Hubble, then you would incur an exponential suppression of this type, okay? So that's all right. However, then you can ask, well, what kind of other energy sources you have which you can tap onto, by which you can excite even heavier particles. And then another source that immediately comes to mind is the kinetic energy of the inflaton, right? So just by observation of power spectra, we know that the slow kinetic energy is pretty big compared to Hubble. And then you can ask, can we tap onto that? Can we extract the kinetic energy by some amount and then excite even heavier particles? And then you realize that you basically have to couple to the velocity of the inflaton in some way, in other words, to the del mu phi operator. And for this talk, we'll mostly focus on scalars. So a first try you can do with the help of this operator is something of this type, where you take the inflaton field, you take the scalar operator, a current-like operator where chi is a scalar field, and you try a coupling like this. Okay, so you might hope that this would give you some non-trivial effect because you're coupling to the velocity of the inflaton. However, as you can show very quickly, is that when you do an integration by parts, this operator becomes a trivial one, and it does not have the effect that you wanted of exciting very heavy particles. However, if you have two fields, then the situation gets more interesting. So let's have a couple of scalar fields, chi1 and chi2. Both have this derivative coupling with some coefficients C1 and C2, okay? Now, just to give you some intuition, let's first consider the case where C1 is negative of C2. So in that case, you can combine these two operators into a very familiar form in which you are basically saying that the inflaton is coupled to the current of the two fields. And in fact, if the chi1 and the chi2 field, they have identical masses, what these kind of couplings is basically means that you have a U1 symmetry and you just have unusual current coupling. Okay, so here's the complex scalar current and you are coupling the inflaton like this. Okay, so till now this is the Lagrangian. So here is the inflaton Lagrangian, here is the complex scalar kinetic and the mass terms, and here is the non-trivial interaction. Now, This is all good, at least at first sight. However, you'd notice that if you do a field redefinition of this type to the chi field, then you can quickly show that this non-trivial del mu phi coupling can be rotated away. And then you basically lose the fact that you're coupling the scalar field to the inflaton velocity. So you can rotate away this entire coupling. And in that case, you do not get any extra advantage in particle production because you're not coupling to the inflaton field in the rotated basis. However, if C1 is not equal to minus C2, which means when you have broken the U1, then this field rotation is no longer trivial. And in that case, you do expect some non-trivial physical effect, okay? So to see that, we will basically take a simpler approach in which we won't pursue the case where C1 is equal to minus C2, but rather we'll set C1 equal to minus C2 so that we can write a term like this. However, we'll still break the U1 in a soft manner, okay? So just to summarize, we'll still have this term, but we'll have an additional term in which the U1 is broken. The advantage of this will be that it will be technically simpler, but it will contain all the necessary physical information. So let's do that. So we have, again, the usual inflaton Lagrangian and the chi kinetic term and the mass term. And here is the U1 symmetric current coupling, okay? So again, the desire is that this is coupling to the inflaton field, so it can extract some of the kinetic energy of the inflaton. We have also written this dimension 6 operator, which would be generically expected just by power counting. But then here is the important part where we have softly broken the U1 that's present on the chi. Okay, so we have just written a term like this, basically a tadpole-like term with some mass dimension cubic. All right, so now to see the effect of the non-trivial field rotation, what you can do is you can again do this rotation that I just talked about. And once you do this rotation, you get rid of this current coupling, but then you modify this term a bit. So basically this term gets modified into this. However, very importantly, this field rotation, it basically puts in factors of e to the I phi in here, okay? So that's the non-trivial thing. So what then happens is that, as we will see in a moment, is that as phi rolls, this term, this kind of exponential, it basically gives rise to a time-dependent coupling between the inflaton field and the heavy field. And we'll see that this time dependence is the driving factor by which we can excite heavier particles. So let me explain what I mean by that. So just to see things a bit more explicitly, what you can do is you can take this factor and you can expand it in terms of the homogeneous value phi 0 and the inflaton fluctuation c. And then just by using the slow roll expression for phi 0, you can write it in a form like this. Okay? So here's the crucial thing. So this particular object, it's a highly, this guy has a large time dependence, especially in the limit where this quantity lambda, which is just given by phi 0 dot over big lambda. Whenever this quantity is larger than Hubble, you have a super-Hubble time-dependent frequency, okay? So it's basically a high frequency source. And then once you expand the rest of the exponential, this high frequency source, they basically act as either high frequency mixing terms between the inflaton and the scalar fluctuations, or cubic interactions, for example, okay? So this particular term in particular gives rise to these kind of mixings and cubic interactions. And as I said, it is basically this operator that gives rise to this, this fast time varying coupling. And as you can expect, there is a fast time variation, and there is now an energy scale, which is lambda, which is super-Hubble. And that's why we have a chance of going beyond the naive Boltzmann suppression. Okay, so we'll basically try to use this large frequency to excite heavier particles. So let's see how that is being done. And the vertices we'll use are basically these two. In the paper, we consider more general vertices, but here we'll just consider this quadratic mixing and the cubic interaction. So with that, let me get on to the results. So as you might be familiar, we will basically talk about 3-point functions. And as you might know, is that in general, there will be 4 types of diagrams at the leading order, the so-called I plus minus ones and its complex conjugate, in which you take one of the in vertices from time ordering and the other one from the anti-time ordering, or vice versa. And similarly, there will be cases, there will be 2 more diagrams in which both of these vertices, they would either come from the time ordering or both of them from the anti-time ordering. All right, so it actually turns out that for our case, it's basically these class of diagrams and its complex conjugate that dominates the answer. And I'm happy to explain this further if you're interested during the discussions. But let's see how we can estimate these diagrams, for example. So the main idea is that because of these kind of large time dependence that I talked about, what happens is that this time dependence, it basically acts as an energy source. Okay, so this time dependence, it can inject energy into the vertices, and as a result, you can produce inflationary fluctuations and the scalar fluctuations. And same is true for these kind of these vertex as well. So you would have noticed that I'm drawing this diagram in a funny way, but here I'm just showing that one part is coming from the anti-time ordering, the other from the time ordering. Okay. Otherwise, topologically, this diagram is same as this one. Okay, so here's the non-trivial physics of energy injection, and let's try to analyze that in a bit more detail. So to see how this is working, you can basically apply a local energy conservation, which is valid on a very sub-horizon scale. So you are injecting lambda amount of energy from this time-dependent couplings, and with the help of that, you are producing inflaton momenta with momenta k3 and also a scalar field fluctuation like this. And once you just apply the simple energy conservation, you can see that the co-moving momenta of these 2 particles at the time of production, they basically are given by this. Okay. And similarly, as we have cut the plus minus diagram, there is also the other half. Here also at this vertex, you can again apply an energy conservation law. And here you would see at the squeeze limit that the co-moving momenta of the inflatons, for example, during the time of their production is just given by this. Okay. So here I should mention that lambda is once again the quantity phi dot over lambda, and mu is basically the mass of this heavy particles, which I'm showing in green. Okay, so one thing that you immediately notice from these 2 expressions is that for any value of mu that is smaller than lambda, this quantity is positive, and that basically means that energy conservation holds. And it implies that the background or the time-dependent couplings, they have enough energy to give rise to these kind of diagrams, and they don't suffer any sort of Boltzmann suppression. Okay, so this is a physical intuition, and we are concluding from here that you can actually produce without any Boltzmann suppression all masses up to the value of lambda. So this was a heuristic argument, but of course we have done a full calculation. And roughly for any value of mu less than lambda, once you carry out the calculation, you basically see a behavior like this of the 3-point function. So it contains several pieces. So let me just summarize them one by one. The first and the second factor, they're basically coming from the vertices and the overall normalization of phi dot. The third and the fourth factor, they basically come from a mix of stationary phase approximation and various polynomial dependencies in couplings. The last factor is the important one. It contains the non-analytic momentum dependence. And here things are a bit different than the usual. So in the usual cases, we just have the mass dependence, which is I'm showing by mu. However, in this case, along with the oscillation of the massive field, we also have oscillations or time dependence of the vertices. And that's why from the eta to the I lambda type of couplings, you get a vertex factor which is given by lambda. So as a result, the oscillation is a combination of mu and lambda. Okay. So once you plug in values, satisfying a bunch of constraints such that perturbativity is holding and also correction to power spectrum is small and so on, you see that this thing that I'm showing in dotted red line, this quantity is basically smaller than 10 to the minus 2 times lambda. However, being totally consistent with effective field theory, the little lambda can be taken to be as big as 60, and this basically means that this factor here can easily be order 1. And when you do a full calculation, you basically get a result like this. So here I'm plotting the magnitude of the 3-point function by extracting this k1 over k3 factor out. I'm just plotting the magnitude as a function of m. And you see for different values of lambda, you can basically have a non-exponentially suppressed quantity up to the value of lambda under consideration. Okay? So it's very flat. It basically shows that the signal does not suffer exponential suppression. All right, so so that's the summary here. So what we have shown here is that with the help of the inflationary current coupling, you can get some non-trivial time dependence in various parameters, especially coupling constants, and that can be useful in exciting very massive particles with masses even up to 60 Hubble, which would have been otherwise extremely Boltzmann suppressed. So with that, let me now move on to the other part of the talk in the small amount of time that I have left. So we have been talking about super-Hubble particles, but let's now ask what happens if the U1 symmetry that I talked about is not broken. In other words, till now we have been thinking about tree-level effects of this type, but let's now ask what kind of signatures we can expect to have if the non-Gaussianity has to be in the form of loops. And for this purpose, we'll demonstrate that the curvaton scenario can be very useful in exciting the loop level in enhancing the loop level non-Gaussianity. So let me first talk about that. So as I said, we have discussed the case of softly broken U1, but let us now make the U1, let us now restore the U1 and ask about loops. So one immediate problem that you hit when you have loops is that there's a big classical correction to the mass that you get. So for example, if you take the inflationary derivative coupling with the complex scalar chi, then by setting both the inflaton to their webs, you basically get a mass correction to the chi fields, which basically go like this. Now, since in this case we can't use, since in this case we have the U1 to be unbroken, we can't use the chemical potential or the fast time dependence in the couplings. So we can no longer go to very high masses. And in other words, we have to stick to masses which are of the order of Hubble-scale. So then in order for this classical correction to be not so small, you basically want this classical correction to be of the order of Hubble square. Okay? Because otherwise you would have to tune this contribution against a tree level value of the mass to get a resultant mass which is of the order of Hubble. So we don't want to do that kind of fine tuning. It's in some sense a classical tuning, and we don't want to do that. And for that, we basically want to demand that this correction itself is of the order of Hubble. Okay? And if we do that, you basically get a restriction that this cutoff scale lambda has to be as big as phi dot over Hubble. And if you then plug in values, you basically see that even for masses which are of the order of Hubble or few Hubble, the FNL or the non-Gaussianity magnitude is super small. Relatedly, you can view this suppression as coming from, as being sourced by a largeness of this parameter or this cutoff scale lambda phi that appears in these kind of couplings. So a reasonable thing you can ask here is that how big do we want this cutoff scale to be? And to answer that, you basically notice that if you want to be consistent with the shift symmetry of the inflaton, you basically want this cutoff to be bigger than square root of phi dot, because otherwise this expansion parameter will be bigger than 1, and the expansion won't be in control. So this is a restriction that you get. However, a big problem with this is that because the same inflaton field houses the field phi 0, which sources expansion, and the same inflaton field gives rise to primordial fluctuations, it basically tells you that any operator which contains the phi 0 part, it automatically contains the inflationary fluctuations as well. And that's why when you put this bound of lambda phi bigger than 60 Hubble, which comes from a consideration on phi 0, this stringent bound, it automatically affects the coupling of the inflationary fluctuations to the heavy field as well. Okay, so there is a restriction that comes from the homogeneous background, and that is ending up affecting the dynamics of the fluctuations. So you can ask, well, can we separate the roles? Can we have the expansion sourced by a field, by one field, and can we have fluctuations come from another field? In which case this stringent restriction won't apply. And that's precisely what the curvaton scenario does. What it basically says is that there could have been a light field, something like an axion during inflation, and the coupling of the axion won't necessarily have a large suppression. And in fact, this quantity, this cutoff scale lambda sigma, it can be much, much smaller than this quantity 60 Hubble. So I am running out of time, so I won't be going over all the cosmology, but the basic idea is that during inflation, the curvaton field is subdominant in energy density, so it does not drive inflation. However, soon after inflation ends, it can come to dominate the energy density, and that's why it can eventually source fluctuations, although it did not source expansion earlier. So then you can repeat the previous procedure and you can couple the curvaton field with various heavy fields. And then to control the EFT expansion, you need the cutoff scale only to be few times Hubble instead of 60 times Hubble. And as a result, being in complete control of the EFT, you can get orders of magnitude larger non-Gaussianity. And for example, you can again couple some charge scalar, some Higgs-like field to the curvaton with a smaller cutoff scale. And that can lead to diagrams like this, where the external lines, they represent curvaton fluctuations. And with that, let me get into the results real quick. So with that, if you calculate a charge scalar mediated loop, then you see that for reasonable values of parameters, you can get FNLs which can be as big as order 1 compared to a value like 10 to the minus 9 in the standard scenario. So this really tells you that with the curvaton scenario, you can have orders of magnitude larger non-Gaussianity, with some of them being even probable by large scale structure. So I don't have really time to go over this, but there have been similar discussions in the literature in the context of fermions and gauge bosons and how to observe very massive fermions and gauge bosons as well. And also related to the curvaton scenario, the modulated reheating can also be used to excite loops. All right, so with that, let me summarize. So we have discussed a simple implementation for unsuppressed scalar particle production with masses up to 60 Hubble. We have We have demonstrated a tree-level effect where the calculation is under control. And also towards the later part of the talk, I have talked about the curvaton scenario, where along with the usual smoking gun local non-Gaussianity, you would expect non-analytic signatures from even loop level particles or loop level diagrams. And many of what we have said could also be implemented within the context of EFT of inflation, although here we have focused on the slow roll picture. All right, thanks a lot for your attention.